Okay, I'm going to continue on with the final chapter that's related to quantum mechanics and chemistry, and that's the chapter, at least the chapter in our class, is the chapter on diatomic molecules. And this is really sort of the last problem where it's the kind of quantum mechanical problem, at least the one I'm going to start with here, the kind of quantum mechanical problem that you could actually probably solve with a pad and paper and pencil and just try to work through this analytically. Beyond that, then we really are in the regime of needing to do numerical calculations. But the goal here is to sort of make you familiar with all of that theory that's needed to see what people are doing in those numerical calculations. So let's just start with what's got to be the simplest molecule you can imagine, which is the H2 plus ion, or the H2 cation. And this is a system where we have only one electron. So there's three particles. There's a proton, and an electron. But what we're going to consider is this single electron that's going to be orbiting around these two protons. And the Hamiltonian that we have to deal with, in this case, is going to include a term that's going to be the kinetic energy associated with the two protons. So this is the momentum operator for proton A and B. And then we're going to have the kinetic energy for the one electron that we're treating in this problem. And then we're going to have the Coulombic interaction of nucleus A with the electron. And then we're going to have the Coulombic interaction of nucleus B with the electron. And then finally we're going to have a Coulombic repulsion term, which is the proton-proton interaction, charge interaction. Okay, so I just summarize these guys again here. So we're going to have two kinetic energies, the nuclei and then the electron. We're going to have the Coulombic attractions of the electron to the two nuclei, the repulsive force. And if I write this whole thing in terms of atomic units, it gets rid of all these constants and we get it into a simpler form. But remember, these guys are all dimensionless quantities here. All right. So if we're going to solve this problem, we need to make some approximations. And probably the first one that everyone does in this problem is what's called the Born-Oppenheimer approximation, or it's a form of the adiabatic approximation. And the idea is quite simple. You might imagine, if you have a proton and they're much heavier than that electron, that the motion of the electron is going to be on a much faster time scale than the motion of the nuclei, right? And it's sort of an analogy, like it's like when I'm driving down the road and you got motorcyclists who are going 5 times faster than the rest of the cars on the highway. It's like the cars are stationary and these motorcycles are moving around between them, right? It seems kind of crazy, but that's kind of the idea that that if you're moving so much faster than the other objects, they just appear stationary from your point of view. So for the electron's point of view, those nuclei, yes, they're moving so slowly that you could have orbited them many times before they actually made any kind of substantial motion. So this is what's called the Born-Oppenheimer approximation. And what we're going to do then is we're going to fix those nuclei, and we're going to solve the Schrodinger equation for the electron in that potential with those nuclei fixed. And then we're going to change the distance between the nuclei and solve the Schrodinger equation again. And then we're going to increase again the nuclei, the internuclear distance, and solve the Schrodinger equation. And we're going to have the Schrodinger equation solved for all these different internuclear distances. And we're going to look at the total energy. And when we find the total energy that's the minimum, that's going to be the energy associated with the equilibrium bond length, right? And then we'll have the wave function and the equilibrium bond length and the total energy in that case. So that's the approach. So we're not going to allow the nuclei to move, and this is going to have a couple effects. The first is, if we fix those nuclei, then the kinetic energy terms for the nuclei is going to go away. That'll be 0 in the problem. The other term is that the nuclear-nuclear repulsion term, the Coulombic repulsion term, now becomes just a constant term and can just be added to the energy eigenvalue, so that doesn't have to be worried about anymore. If if we do this problem that way. So if we make this approximation, then we can look at the electronic wave function here as being a solution to where we just have kinetic energy for the electron and then the Coulombic attraction to the two nuclei. So H psi is equal to E psi. Excuse me. So what we're going to do is we're going to do this, and we're going to solve as a function of the internuclear distance. Now, when we do this approximation, we're going to do this in a way that the total wave function is going to be approximated as a product of the electronic wave function with the nuclear wave function. Now, we've talked about nuclear wave functions. In this case, we're talking about it might be something like the Hermite polynomials if we're thinking very low amplitude vibrations, low quantum numbers. This could be a Hermite polynomial, and this would be the solution that we get. But right now we're just leaving it in a very generic form like this. And so, one of the things that's going to be going on then is if we assume that the electrons are moving really slowly, even though the electron wave function depends upon the distance between the nuclei, we can assume that when we get to this term right here in our Hamiltonian, when that gets applied onto the total wave function, that this slides right through, and we only operate on that guy. Now, you might think, wait a minute, that guy depends on the internuclear distance, so shouldn't this guy apply onto that? And the answer is yes, technically it should, but our approximation is that it's varying so slowly, this wave function with R, that we can just slide it past, and it's not going to be a big contributor. So in other words, when we did this, we just said that this part of that operation ended up being 0, and all we're left is this, okay? So this is a part of making that Born-Oppenheimer approximation, that this operator applied to this combined wave function leads to this result. Okay, so that's then the groundwork for the Born-Oppenheimer. Let's go back now and take that wave function and plug it into the full Schrodinger equation. So remember, that's the full Schrodinger equation in atomic units for the problem. And when we do that, what do we obtain? This is what we get. Okay, so let's go a little slowly here, but so remember again that the wave function for the electron slid past this guy, and so we just have this. And then we have the part that applies to the electronic wave function, which is right here. Okay, and then we have, this is the Coulomb term between the two nuclei, and then we have the total energy on this side here, and there's our wave function. So what we're going to do is we're going to take a look at this, and we see that this is the electronic part, this is the electronic wave function, electronic Hamiltonian. That part, H psi, is E psi, right? So in other words, if we fix the nuclei, and we said that they weren't moving, and the electron was just a problem with a potential of just two fixed positive charges, then this solution here, this H psi is equal to E psi, we can just go ahead and replace this whole thing with just E psi, right? So what I've done is I'm just going to take all of that there and just replace that with this quantity. So now, when I bring this all together, I now have this guy, which is still out there. I have the kinetic energy for the nuclei. I have this term, which is the electronic energy for that fixed distance. And then I have the Coulombic repulsion term between the two nuclei, operating on the wave function, and then I get back the wave function times the energy. And I'm going to pull the psi function out because it goes on the other. It doesn't matter. These are not operators on this side. So the point is I can divide by that guy, and I get out of all this guy. So now the psi for the electron is gone, and I now have the Schrodinger equation for the nuclei moving in a potential of these fast-moving electrons. So the potential that the nuclei see is not just the Coulombic repulsion, but there's also now the electron energy term, which adds to this, which makes this the effective nuclear potential. So in a way, this term, is just going to push them apart, right? What this does is it counteracts that guy. That's the glue, right? The electron glue, and it's part of the potential that's going to pull these guys together and allow them to form a bond. Okay, so this is the interaction. This describes the Schrodinger equation for the nuclear wave function. So the general strategy then is that we need to find that guy, which we get by solving the Schrodinger equation for a fixed internuclear distance, and we do that for all possible values of internuclear distances. And then we add that guy to this guy, and that gives us the potential for solving the nuclear wave function. Okay, so it's two parts back and forth. So we're going to just solve the electronic wave function for all these different internuclear distances, and when we're done, we're going to have a potential energy surface that we can then use to calculate the nuclear wave function solution. All right, so let's move on then. Let's just focus on the electronic part. Okay, we're actually not that interested in what the form of the nuclear wave function is, because it's really sort of, you know, a more complicated version, but so we already treated that when we talked about vibrations, right, of molecules, or at least in the harmonic oscillator case. And so now we're going to focus on the solution of the electronic part with this fixed internuclear distance. So R now, the big R becomes this parameter that is part of the problem. Okay. Now, the tricky part now is that when you look at this, this is an electron moving in the potential of two fixed protons, right? So this doesn't have any spherical symmetry, right? And so you think, all right, probably don't want to use Cartesian coordinates, but you look at this problem and you think, I'm not sure I want to use spherical coordinates either, because now I have like a proton here and a proton here. It's like I got an origin here and an origin here and an electron that can move around them. So that's, the spherical coordinate system is not going to work either. So what coordinate system can we use? Is there a coordinate system that we can use to do this? And actually there is. Not something that you probably would have thought off the top of your head, but there's a coordinate system called a spheroidal coordinate system. And it's described this way. It's got two foci here, 2 points here, which is, in our case, is going to correspond to the location of the two nuclei. And so this is our z-axis here. And we're going to define, so just like we did a transformation, say, to polar coordinates, we'd have r and theta, right? In this case, we're going to transform into two coordinates, and they're going to be lambda and mu, right? And r is this fixed distance between the two nuclei. And lambda is going to be a coordinates defined as the distance from the electron to nucleus A plus the distance to nucleus B divided by the distance between the nuclei. And mu is going to be R A minus RB divided by the distance between the nuclei. So this is called a spheroidal coordinate system. And so these lambda coordinates, that's these ellipses here. Okay, so the ellipses are lines of constant lambda. Okay, and they're ellipses have these foci. They have the same foci, so that's why they're called confocal. And then the mu are these guys here. They're hyperbolas, and these guys then sort of have this behavior where they sort of become more and more curved as you move out away. Okay, but their foci also are these nuclear positions. So these guys form a, so to speak, grid. This is an orthogonal system of curves, which we can define our wave function at every one of these points where these in this coordinate system. All right, now this is crazy. I know this is crazy, but trust me, it works, and it will give us some insight here. All right, so this variable lambda is, okay, this is these ellipses here associated with these ellipses. This goes from a value of 1 to infinity. And this, as I said polar coordinates before, because I was actually knew that this is sort of the analogy here. If you think about, you know, how far out you are in polar coordinates from the origin, then that's what this lambda is sort of telling us. as you get to further and further ellipses that are further and further out, it's kind of like the analogy of the R in polar coordinates, except instead of one origin, you have these two foci. And the variable mu, which are these hyperbolas here, that they actually go from -1 to 1, all right? And in a way, then these guys sort of play the role that's similar to cosine theta in the polar coordinates system too. So it's kind of like a polar coordinate system, except you got, instead of one origin, you have these sort of 2 points that your whole thing is centered around, all right? Now, we actually have to solve the problem in 3D, and what I showed you so far was just 2D. So if you take this whole thing and you add a new variable, phi, so that you can rotate it about this, then you have a 3-dimensional coordinate system. So you have lambda, mu, and phi, and you can specify any coordinate in this space. So the ellipses then generate ellipsoids when you rotate them. So that's what I call confocal ellipsoids, because all the ellipsoids share the same foci. And then the hyperbolas form a set of these guys in 3D, as you rotate, form a set of sheets. So what I call a family of hyperboloids. And I'm saying the pronouncing these right. And then these phi's then will form, the surfaces of constant phi will be half planes, which sort of end at the z-axis, and they pass through all the x-axes there. So just to show you, this is what I meant by a 3-dimensional hyperboid. Okay, so that's what the shape looks like. So you imagine rotating this guy in 3D, and that's your 3-dimensional coordinate system. All right, so that's the coordinate system we're gonna transform our Schrodinger equation into, our wave equation into, in order to try to find an analytical solution. Okay, so we want to transform this guy, x, y, and z, RAB, to mu, lambda, mu, phi, and RAB. Now, I'm not going to get into the details. I'm just going to show you just the sort of the tip of this problem, and which is just that, the wave function, if you convert it into this form, you can actually write it as with separation of variables as a function of lambda, a function of mu, and a function of phi. And once you do that conversion of the wave function, your conversion of the Hamiltonian, you plug them in, you can get 3 separate differential equations which you can solve. And I'm not even going to go close to that to even suggest. I'm going to show you how that's done. You're certainly welcome to try, and you can find it in books, but we're going to get 3 ordinary differential equations, and I'm just going to talk about the solutions. I'm not even going to show you the differential equation or anything like that. So we're just going to look at the results, all right? So first of all, the one I'm really interested in is this solution as a function of phi. As you might imagine, it has a very simple form. It just looks like 1 over square root of 2 pi e to the I m phi. And these are eigenfunctions of LZ, okay? And each of the different m values, magnitude of n, have a different energy. And when they have plus or minus m, the same m value, whether it's plus or minus, those are going to be degenerate states. So in the solution to this problem, the wave functions for the hydrogen molecule cation, we're going to be looking at wave functions which are labeled by different m's. And m equals 0 is going to be called a sigma wave function. And when m is equal to plus or minus 1, it's going to be called a pi wave function. And when m is equal to plus or minus 2, it's going to be called a delta wave function. All right? So we're going to be doing kind of like we did with atomic orbitals, S, P, D, except we're using Greek letters, so sigma, pi, delta. We will also label these states by how they behave under inversion symmetry, so inversion through the origin of the problem. So when you take R and you go to minus R, does the wave function change sign or not? So, and we're going to give labels of U if they have odd symmetry, and G if they have even symmetry. So that's Unjard and Girard if you speak German and I don't. So these are the subscripts for even and odd. Okay. So what we'll see then is a whole bunch of functions which are going to be, where their m value is going to be given by some symbol, sigma, pi, or delta, and their symmetry is going to be given by a subscript, g or u, right? And we'll be looking at wave functions, and those will be the labels that you see on these wave functions. So here are the solutions for the energies as a function of different internuclear spacings, right? So as I said, we're going to solve the wave function for different internuclear spacings, and we're going to get an energy for each one. And now this is a plot of those energies as you vary from the internuclear spacing going from 0, which means the protons are right on top of each other, out to 14 Bohr radii or further if you like. And so here are the labels on these guys. So the lowest one, energy 1, is called a 1 sigma g, and then we have 1 sigma u. So this is the lowest energy one has even symmetry, and this one has odd symmetry. And then we move up in energy, and you can see that down here, where we're close to the energy minimum, this is where the equilibrium bond length would be, right? This is the lowest energy. Then we're going to have the energy levels for the other guys. And so you can see up here are the other states. There are some, 2 sigma g's, 1 pi g's, 2 sigma u's, and things like that. We'll talk a little bit about those at some point, but those are we're going to focus primarily on these lower energy guys here. Okay. So the first thing we see, as I pointed out, is that the minimum in the energy is down here around 2 atomic units, so 2 Bohr radii for the distance, and that's the 1 sigma g state. That's the ground state. And you can see that as we increase the distance between the protons, that the energy goes up, and eventually it levels off at 0.5, minus 0.5 Hartrees, okay? And that should make perfect sense, right? Because if you had one electron and 2 protons, and you pulled them apart, then one of those electrons is going to be orbiting, the electron will be orbiting one of those protons, and so you're going to have the energy of isolated hydrogen atom and then a proton. And so what we see is that this is going towards the energy of an isolated proton. So if you go back and look at the energy of an isolated hydrogen atom, a 1s state, it's an energy of minus 1/2 Hartree there. Okay, and then we can look at the difference in energy between here and where the minimum is, because this is where it's infinitely separated. This is the stabilization we get by forming the bond, and so that's down about 0.1 Hartrees. So that's the binding energy that we get. So that's the electrons form that glue that hold the nuclei together. Okay, and the experimental values that you get for the equilibrium distance are 2 Bohr radii, so like right spot on, and the binding energy is 0.102 Hartree. So that solution with the spheroidal coordinate system worked out analytically, and we didn't do it, but we just started just a little bit down that road. If you finish down that road and you work out the whole thing, you end up with these curves, and you get values that are pretty much in agreement for what we know are the equilibrium distances and binding energies for a hydrogen H2 cation, right? So now looking at this, we're looking at sort of the behavior as r goes to infinity. There's also another interesting behavior as r goes to 0, but it's not. In this plot I have the internuclear repulsion of the electrons of the nuclei together. If I take out the repulsion energy of the nuclei, so that I don't consider the fact that the nuclei are repulsed, but I just bring them together. When I bring the 2 protons together, I've actually formed a helium nucleus, right? So if I form a helium nucleus and the electron is orbiting a helium nucleus, my solution should go to the solution for a helium atom with 1 electron, helium plus. And in fact, actually it does. So in the solution that, if you took out the internuclear repulsion term, when R goes to 0, you get a helium nucleus, and you get an energy of -2 Hartrees, which is the solution you would get for a helium plus atom, right? So for a single electron bound to a nucleus. So it's got everything it needs in it. You know, you pull it apart, and you get an isolated hydrogen atom and a proton, and this guy's got -1/2 Hartree, and if you bring them together, you get the solution, which is for a helium plus cation. All right. So it's working really nicely. All right. So here are the solutions for the wave functions. So here you can see this is R equals 8. So this is far away. Remember that the distance that was we go back here. So the distance that was R equals 2 was near the equilibrium distance, right? So here is R equals 2. So this is the ground state wave function when we're at the lowest energy. So this is when you're pulled apart, and then you can see here, this is you're getting closer, and you can see the overlap between those wave functions. And then if you keep going, keep pushing them, you get over here where you can see this is where the two protons, this is R equals 0, the two protons are right on top of each other. Right? And actually that solution there is pretty much exactly what you would get for the helium plus wave function there. All right. And for when you're far away, so as I say, you're about out to 8 angstroms, then what you have is a solution for the wave functions for when the two isolated hydrogen atoms, right? So the wave function shapes are there. Doesn't mean that they're occupied, right? I can calculate the shape of a wave function, whether the electron's in it or not, and that's what we have here. So we have the two wave functions. This is the low energy state. That's the excited energy state, the two lowest ones there. Okay. So what we get then when we go to R equals infinity, it really looks like just, you know, if we keep going, we would just end up with just two 1s orbitals just sitting far away from each other. And as you look at this, you think, okay, you know, only one of these is occupied, but you can look at how these guys combine, and it really looks like you're when you're far away from each other, that you have something that looks a lot like you just took something that looks like the individual 1s orbitals and just added them together. So this was this guy where they're both positive is this solution, and then when we have the odd solution, and we just took one and we made it negative and added it to that guy. So when you look at this result, you think, well, that's kind of cool, because it says that I could really think about this problem from in the limit that R is far away is just two s orbitals, and as I bring the two s orbitals together, they just sort of constructively or destructively interfere as they meet and form this molecular orbital. I mean, it's not the solution exactly the same as the solution we got, but it seems to look like that solution, right? In other words, it's not a bad guess for what the molecular orbital would look like for the H2 plus molecule. It's just taking a 1s orbital here and a 1s orbital here and just bringing them together and letting them constructively and destructively overlap, all right? So, as you might imagine, you know, I just use that word a good guess because you can think, well, I really don't like these elliptical or these spheroidal coordinates. This actually only works for H+. So maybe I can take this approach of just taking atomic orbitals and bringing them together to form linear combinations that have constructive and destructive interference that make molecular orbitals. So this approach is called the linear combination of atomic orbitals to make molecular orbitals. So it's called LCAO. And it's a guess. It's all it is. It's just saying that's not a bad idea for a starting guess. And what we're going to do is we're going to put some extra parameters in those functions to make them adjustable, and then we can use the getting tired here. Sorry. We can use the variational principle. Oh my gosh. All right. it's 5:30. You're in the exam, and I'm still trying to finish up this lecture before I leave on Sunday. So yes, so we're going to use the variational principle. So let's talk about this approach, this linear combination of atomic orbitals. And so using the variational theorem, I just went ahead 2 slides. Using the variational principle, we're going to just say that our guess is just a linear combination of atomic orbitals. Right? And we have these unknown coefficients here. That's the approach we're going to use. Now, there are 2 adjustable parameters here, CA and CB. So those are the 2 things we're going to vary in our variational approach, is how much of each of those guys that we have to add. And of course, the variational theorem tells us this, and so we're going to go ahead and plug it in. But of course, we got to be careful because the way I've written this guy is normalized, that's normalized, but adding them together is no longer going to be normalized. So we're going to have to normalize our guess. So we'll have to do that integral and divide by that in order to keep everything normalized. All right. So that will work. And once I plug in my guess into this, I get this. All right. And now we need to do 1, 2, 3, 4 integrals there. And they're all a little different from each other. So let's try this. And the beauty of this is this will be more general than just the H2 plus molecule. So what we see, first of all, is that this guy right here, which is the Hamiltonian of evaluating between 1s on A and 1s on B, we're going to call HAB. And this guy, which is just the integral of 1sa, 1sb, we're going to call SAB. All right? And this guy is going to be called the overlap integral. And if we make these definitions, then we can rewrite that expression before in a little shorter form, which looks like this. All right? Now, what we need to do is find out where the energy is a minimum. So we need to take the derivative with respect to our variational parameters. So we're going to do this by doing a little math trick here. We're going to move the denominator, this guy, over to the other side. Okay, so just go back and check this very carefully. And then I'm going to take the derivative with respect to CA of both sides of my equation. And that's going to give me the derivative of stuff inside here times E, and then this stuff inside here times the derivative of E, and then on the same, it's going to give me 2CA, HA, and then 2CB, HAB. And then I'm going to do the same thing with respect to CB, and then I'm going to get, a little rearranging, setting them equal to 0, these guys equal to 0, I'm going to get this set of simultaneous equations. All right? So now I have 2 equations, 2 unknowns. So in a matrix form, it looks like this. And if you know anything about solving these linear algebra problems, then we just need to solve this determinant. And this we're going to make it a little bit easier because we're looking at hydrogen and hydrogen. So we're going to, A and B are actually the same nucleus. So we're just going to make that substitution and call that alpha. And we're going to take the A and B term and call that beta, because that's the one between the 2 atoms, 2 nuclei. And then we get this form of it. That's our determinant. And if you expand out the determinant, you get this, which is set equal to 0. You set that equal to 0, and you can solve this equation, and you get the energies. So you get 2 solutions for this equation. You get one solution we'll call the plus solution, which is alpha plus beta, divided by 1 plus s, it's the overlap integral, and then E minus, which is alpha minus beta, divided by 1 minus s. Okay. And if you put those back into the simultaneous equations, you can find actually that there's a constraint then that Ca is equal to Cb. For E plus, and for E minus, Ca is equal to minus Cb. So that means that the 2 wave functions that are our guesses are, after they've been through the variational theorem, have this form. And we just have this coefficient C, which is just a normalization factor. So if we normalize these guys, that's what we get. And there you have it. We've solved for the wave functions in terms of the atomic orbitals with just coefficients in front. If I plot those guys, they're the ones in the dashed lines, and compared to the exact solution, you can see it's not bad, right? It looks like it has the right shape. It's a little bit lower in amplitude. Over here, it seems to be a little bit higher in amplitude for the anti-bonding state, or the first excited state above the ground state. But this is pretty good for such a simple idea. Just two atomic orbitals brought together with linear coefficients in the variational theorem to form the molecular orbitals. And what's nice is, I said, this is general. This will work for multi-electron atoms too. So we have to figure out those integrals, though. I left those to the last bit here. So there was this overlap integral between the orbitals on the two different nuclei, right? So when we bring it in, we expect that orbital overlap to increase. So this variable, this integral, should get higher and higher. And if you actually insert the form of those wave functions, you get an expression that looks like that. And I'm going to leave that, sort of as an assignment you can do. If I plotted that, then you see you get the overlap integral as a function of r in terms of Bohr radii. And so you see that it just drops down, as you might expect, because as you get far away, and the limit that you go infinitely far away, then there should be zero overlap. So that integral goes to zero. And of course, when you go to r equals 0, then you have maximum overlap, and that's when the integral goes to 1. So that behaves in a way that sort of makes sense. The other one is called alpha is called the Coulomb integral, and to do that, we're going to have to plug in the Hamiltonian here, and we'll do this in a way that's sort of a little trick here. We're going to, since this is A and A on both sides, I'm going to rearrange this Hamiltonian so that it looks like this guy is just the interaction with A, and this guy is the interaction with B, and this is the repulsion term. So I'm going to rewrite it this way, where this looks like it's just interacting with the A nucleus, or this way, where it looks like it's only acting with the B nucleus, and these are the other terms there. So if I do that, then I can plug this guy in this form over here, and then I break it up into these three terms. So this is the part that, well, that's easy now, because that's just the energy of that 1s orbital, right? Because that's all we have there. And then these guys I have to evaluate, and again, here's the result. I'll let you work that out. But that's the whole expression for the alpha. So it's sort of this first term is the energy of the 1s plus this term from these cross, with this 1 over RB evaluator between those orbitals on the other side, and 1 over R, capital RAB, which is the repulsion term. All right. Okay, so this contains the energy of the 1s orbital, the attractive energy of nucleus B for the electron, that's this guy, and then the repulsive force of nucleus B with nucleus A. And this plot looks like this. This plot starts out, it actually goes to infinity at r equals 0, as you might expect, because of the repulsion term. And so as it goes from infinity at r equals 0, and it goes down to minus 1/2 in terms of Rydberg's at infinity there. All right. So with this then, you can see that this term, this alpha term, just goes down, but actually never minimizes. It never bottoms out. It just goes down, progressively continues to go down. So it just levels off at minus half. So that term by itself in this expression for the energies is not the one that's bringing you to a minimum. It's not leading to this guy being lowering energy than that guy. So, okay, so what we need to figure out is, this beta term, because that's where really the story is coming into this. So this alpha is not really giving you any stability. It's the beta term, what's called the exchange integral, for a reason that will be sort of obvious. But this is the Hamiltonian between the wave functions on the two different atoms. So when I take that guy and I use the same approach as I did before, I'm going to put HB in here, and I evaluate this guy. I'm going to get three terms, and now when I evaluate this guy, it's going to come out a little different. And now I'm going to have the energy of the 1s orbital times the overlap integral, and then this term here, and then the overlap integral over the r. So this is the repulsive term times the overlap. Right? And that term, again, I'm going a little fast here, so feel free to stop the video and take a look at this again. But this term is the one that drops down and reaches a minimum and then comes back up. So this is the exchange guy. This one goes to a minimum in energy. And this is the one that creates the stabilization that allows the electron to move back and forth. So it's the exchange between the two nuclei that allows them to sort of glues them together. So both A and B are negative. So if this is negative and that's always positive, then the lowest energy is going to be the E plus state, as we saw earlier. Oops. And if I put, so I put the total together here. So this is the total energy with all those terms combined, and E plus and E minus. Then you see that the minimum, kind of shallow in this picture, but there it is. They're at 2.5 angstroms, at Bohr radii. 2.5 Bohr radii is where it is. And the binding energy works out to be 0.0648 Hartrees there. So the difference between infinity and down here. Now you might remember those numbers from the exact solution. So the bond length that we found in the exact solution, which agreed with experiment, was shorter. This approach gives 2.5 Bohr radii. And the binding energy is lower. So before we knew experimentally it was 0.102 Hartrees, we get a value that's lower. So this isn't as deep as it should be compared to the infinitely separated. All right. And then for the antibonding, we have the other energy here, and this one, of course, is going to be give no stability because it raises. The beta is going to raise the energy because this is already negative, so then you put a negative sign in front of it, and now you're going to start bringing the energy up. So that's going to destabilize a molecule. If you put a molecule into this energy, then it would be higher in energy than being sort of separate ionized. You know, there was H plus and a hydrogen atom would prefer to stay apart than to bond together with just one electron in this guy.